All right, welcome to these slides on probability. This will be a fun one. So I have a lot of topics, surprisingly, about probability that I'm required to teach you. So let us begin first with some jokes, because I'm sure we've heard the idea about correlation is not causation, and that is all about probabilities, right? So let me just show you this to get us off to a fun start. So here is a very interestingly correlated piece of information. It looks like as cheese consumption goes up per capita, that's in red, so it looks like over time in the early 2000s, people slowly started eating a bit more cheese than usual, and also the number of people who died by being tangled in their bed sheets over that same period of time pretty much followed the cheese consumption graph. So, it seems like cheese causes you to get tangled in your bed sheets and die, doesn't it? No, that is not the same, right? Correlation. We found a correlation. We did not find some proof that those two things cause each other. Yeah. Another example, global average temperature versus the number of pirates. So over time, these are years, it looks like the global average temperature, it's definitely increasing. That's unfortunate. But the number of pirates, approximately, is decreasing. So it looks like there's an inverse relationship. So if we want maybe to lower our global temperature again, we better have more pirates. Yeah? So that could be one conclusion if you didn't understand that correlation does not mean causation. So that's like intuitive probabilities. We're going to get into some very fancy math, and so I wanted to at least lead up to it with this stuff. Okay, so let's get to the main event, and that is of course a pun, because the very first term I want to teach you in probability is event. Okay, or I guess experiment, which we'll get to event. All right, so an experiment, something you want to do, right? It's a procedure. It results in one out of a number of possible outcomes. Yes? So for example, maybe one experiment is you flipping a coin, right? Boop, here's a coin. Maybe it's heads up right now. If you flip that coin, it will either land heads or tails. Those are your outcomes of those are the outcomes of your coin flipping experiment. Okay, so it could either be heads or it could be tails, and that is the outcome. The set of all possible outcomes of your experiment is called the sample space. Okay, so the sample space of flipping a coin is the set. Well, it could be heads or it could be tails. That's all the possible outcomes. And then finally, a subset of the sample space we call an event. That's something that might happen, maybe multiple things that we all want to have happen. Okay, so one event, for example, is the event where we get heads in our experiment of flipping the coin. And so it's a subset of the sample space. So it's the set containing just heads. That's a subset, right, of the set heads and tails. And this is maybe the experiment, or this is the outcome that we want to have happen. That is an event that we would like to see take place. Okay? A subset of the sample space is called an event. And so we're making all this very formalized with set theory, as we like to do. All right? So that's the first thing. Now let's talk about probability distributions. So a probability distribution, maybe that should also be in bold, over a sample space, and we're going to call the sample space S. It's a set, right? It's a set of all possible outcomes of your experiment. A probability distribution over that sample space is a function. A function taking a outcome, something in S, to a number between 0 and 1. That's a probability, right? Such that the sum of all the probabilities over everything in the sample space, that's what this summation notation is saying, sum up all the probabilities of all the different outcomes in the sample space, apply your p function to them, they better all add to 1. Okay, that's what it's saying. So here is, for example, a probability distribution of like a fair die. If you're rolling a die, right, you have 6 options. You have boop, boop, boop. It could be 1, 2, 3, 4, 5, or 6, right? Those are your outcomes. And the probability of each outcome, this is the probability of each outcome, it should be, for each of them, if it's a fair die, it's 1/6, right? Should be 1/6 chance of landing on a 1, 1/6 chance of landing on a 2. But in total, no matter what it is, that's 6/1/6, right? The total probability distribution, all those things in that function, they better sum together to be 1, right? Whatever the probabilities of each individual event are, they better sum together to be 1, because you better have talked about every possible thing that could happen, right? Perfectly probable is the number 1. Never happening is the number 0 in probability. Okay, so that's the probability distribution, and that's a function over the sample space to the interval between 0 and 1. It's like, oh, if it's 0, it's not at all probable. If it's 1, it's always going to happen. If it's 0.5, it might happen sometimes, right? And you can have different probabilities, but it's got to be between 0 and 1. Okay? And then finally, if you have an event which is a subset of your sample space, like maybe I only want, when I roll a die, I want to know, like, hey, is my die going to land on 1 or 2? Like maybe I want both of those as valid options. Like 1 is okay, 2 is also okay, but maybe I don't want to see 3 or any other number. So you can ask for the probability of an event as well, and you can use your original probability distribution. You just add together everything. It's like, what's the probability of me seeing a 1 or a 2? That's an event, right? It's a subset of the outcomes, the entire sample space. That's just going to be equal to, at least for our case of a fair die, that's going to be the probability of you seeing a 1 plus the probability of you seeing a 2. Yeah, that's how that works. And I think I need to draw some more, so let me put this below. There we go. You could also have a weird-looking probability distribution. Like maybe you have an unfair die. Like it is like a lot more probable that it's going to land on a 2 rather than any other thing, right? That is possible, and that is kind of like how the probability distribution for that unfair die would work and how it would look. Okay, so that's that. And you can talk about the difference between a fair die and an unfair die by getting into, like, is the distribution uniform or not? Okay? In a uniform distribution, that is when every outcome has the same probability, like for a fair die. It's a 1/6 chance of you landing on anything. For flipping a coin, it should be a uniform distribution as well, right? So you could either get heads or tails if you flip a coin, and it should be the case that the probability of you getting heads is equal to the probability of you getting tails, right? 0.5. That's your probability. That's a uniform. That's another uniform distribution, okay? Every outcome has the same probability there. And yeah, it's really nice when you have a uniform distribution because you can calculate what is the probability of each of these. Because if you know every outcome, like there's 2 outcomes, you just divide 1 by 2. You just divide 1 by 6, and that gives you the probability of each individual outcome. Okay? So, yeah. Coins, for example. Coins have a uniform distribution. Yay. And that is a correct probability distribution because the probability of each outcome summed together is 1. The probability of you getting heads, 0.5, plus the probability of you getting tails, also 0.5, sums to 1. That covers every possible outcome. Okay? So a lot of terms that I'm sure you've heard before, but now we're getting very fancy with them. We're using set theory. So that's events. And now let's talk about combining events together. So you might have multiple events, multiple separate events that you care about, okay? So 2 events, we call them mutually exclusive if the 2 events are disjoint, right? So for example, maybe one event is the die, you rolling it and it lands on 1, 2, or 3. And another event is you rolling the die and it lands on 4, 5, or 6. You see how those are disjoint events? Those are called mutually exclusive. They can't both happen at the same time, okay? But you can also make events that have overlap, and those are not mutually exclusive. They might, like, overlap and have the same piece happen at the same time, okay? So you got to keep that in mind. If they're mutually exclusive, it's very easy to add together probabilities and consider the union. But if they are not, and if they share things, you have to do that principle of inclusion-exclusion here again. Okay? So the union of two events, the probability of that union happening, the union event happening, is the probability of the first thing happening plus the probability of the second thing happening minus the probability of their intersection. I hope that makes intuitive sense. And of course, this is going to be 0 when those two events are disjoint, when they're mutually exclusive. So 0 when they're disjoint. Okay? So that's the union of events, and you can come up with the probability of the union happening, all of those different things in those events happening. You can also come up with the complement of an event. That is the probability of that thing not happening. So the complement of an event E, we say, is E bar. Let me move that so you can see the bar. That just means everything other than the stuff in E happening, yeah? It's just like our Boolean algebra all over again. So the probability of E not happening, right, is every other thing. So P of E, take that probability and subtract it from 1. It's every other thing happening, okay? So for example, if our event was me rolling a 1, 2, 3, or a 4, that's my event E. E bar would be everything else, rolling a 5 or a 6, yeah? And so likely the probability is going to be everything else, right? 1 minus that thing, the probability of the original event. So that's how you come up with the complement event and the complement probability. And this is a very useful concept, in fact, because I want to teach you about the birthday paradox, if you haven't heard about it before. It's very, very cool. So let me ask you this. What is the probability that in a group of n people, like a class of 50 students, for example, what is the probability that at least 2 of those people have the same birthday? We can actually come up with the formula for this, and it's surprisingly small. You only need a few people to come up with a very high probability that 2 of those people have the same birthday. For example, if you have a group of 23 people, it's already a 50% chance that those, like 2 of those people, a pair out of them, share a birthday, which seems very illogical. Weird. And the reason the complement's so nice is because it's very hard to come up with the probability of this normally, but it's actually really easy to find the probability that nobody in a group of n people share a birthday. That's a very easy probability to find. Okay? That's super nice. And so let me teach you how to find this, solve this birthday paradox, find the probability that a group of n people, that you find a pair of them with the same birthday. And so we need to make a few events, okay? The event 1 is the person 1 has a birthday. Then event 2 is the person 2 has a birthday on a different day. Then event 3 is person 3 has a birthday on a different day from the previous 2. I want to combine all of these events, and that's how I can find the probability that nobody in a group of n people share a birthday. We have to take the probability that the first person, well, they could be born on any day, right? For example. So that would be, for example, if n is 23, what's the probability that nobody in that group shares the same birthday? You have, well, the first event is that, well, person 1 could have any birthday, doesn't matter. It's 365 over 365. Let's not care about leap years for this example. And that's fine. And then we have to take the next event. What is the probability that the next person in that group of 23 people, that person has a birthday on a different day than everybody else? And so, well, we've picked a day for person 1 to have a birthday. You can't use that day anymore if you're claiming that nobody shares a birthday. So you have 364 options out of 365 now. And because these are independent events, we can multiply them together and get the probability of their combined event. Okay? We'll talk about that more later. But that is the idea. So what's the probability that the third person does not have a birthday among everybody else? Well, you've picked 2 birthdays for people now. you now need to choose another day than that. 363 out of 365. That's event 3. And so the probability that nobody in a group of 23 people share a birthday is 365 over 365 times 364 over 365 times on and on until you get to 365 minus 23 plus 1 over 365. That's the probability that nobody in a group of n people share a birthday. Does that make sense? And then, if you want to find the probability that at least 2 people, some people at least, share a birthday, you just take the complement of it. Does that make sense? You calculate 1 minus that probability that nobody shares a birthday. That will give you the probability that at least 2 people, maybe more, have the same birthday, that there is something in common. So it's very easy to talk about this and then find the complement. That is a very useful thing to do. Okay? So I have a cute example in Racket of the birthday paradox. So let's run it with n being 23. It's going to calculate... I guess I just need to call it, sorry. Birthday paradox of 23 people. And so it's just going to multiply together 365 over 365 times 364 over 365, on and on forever. It's going to build up this probability that everybody was born on a different day, and it will talk about this probability of that complement of everybody born on a different day, and then the probability that that not everybody was born on a different day, that there is some overlap. That's subtract it from 1. Yay, so 23 is the first whole number that works out. So the probability of the complement that nobody shares a birthday is 49%, and then the probability that some people do share a birthday is 50%, which is really cool. Let's see here, display. Can I do an empty line maybe? If we had a class of 50 students, for example, let's try it there. Oops. I just wanted an empty line there. With a class of 50 students, crazy enough, the probability that nobody in the class shares a birthday with anybody else is 3%-ish. There's a 97% chance that there are at least 2 people that share a birthday. So this would be fun if this was an in-person class. I could ask you guys, hey, tell me your birthdays, and it would be very, very likely that 2 people in the class share a birthday right now. That's really cool, huh? And so that is how you can combine events. You can take the union of things, you can make a new event that is the complement, find its probability, and then if you have independent events and you want to know the probability of one event happening and another, you can multiply them together if they happen to be independent, we say. Okay? We'll get to what that means later, though. All right. So now I have a question for you. Try this. You have a drawer, and again, you're silly and you do not sort your socks. So you have n white socks and n black socks sitting in your drawer. Each white sock has its own little design, and each black sock has its own design. Okay? 2 socks are selected at random from the drawer, so you're pulling 2 random socks out, and every way of selecting 2 socks, like you're shuffling the socks with your hand before you grab them, so every way of selecting the 2 socks is equally likely, and the order that you grab those socks doesn't matter. Here's my question for you. How many ways are there to select those 2 socks? Okay? White socks and black socks. Every white sock is different, like maybe they have numbers on them. Every black sock is different. Maybe they have numbers on them. So how many ways did you come up with? Well, order doesn't matter of selection, so it's going to be a combination, right? How many ways are there to select the 2 socks? Well, how many socks are there to choose from? 2n. How many are you choosing? 2. See that? So that's the answer there. Okay, next question. How many ways of selecting the socks result in 2 socks of the same color being chosen? Okay? Doesn't matter that they have unique designs on them, just I want 2 black socks, 2 white socks. How many ways are there to do that? So, the question is, how many ways are there to select 2 white socks, for example? Well, how many white socks are there? There's n of them in the drawer, and I want to select 2 of them. So there's n choose 2 ways to do that. Plus, how many ways are there to select 2 black socks? And choose 2 again. See that? So that is 2 times n choose 2. And that's going to be, what? N times n minus 1 over 2 factorial times 2, so the 2's cancel out, and so the answer to that is n times n minus 1. That's how many ways. And then finally, tell me the probability, this is the new thing, what's the probability that a randomly chosen pair of socks are the same color? Try and simplify your expression as much as possible so that there's no choose inside of it, okay? What's it going to be? So, let's see here. So remember that n choose 2, the reason like this expands is because that's equal to n times n minus 1 over 2 factorial, which is just 2, right? 2 times 1 is still 2. We need to then go and calculate like what is 2n choose 2, because we're going to need that in just a second. 2n choose 2. That is equal to, well, it's 2n times 2n minus 1 over 2 factorial again, which is 2. But we can like cancel one of these 2's if we wanted to. So it could be n times 2n minus 1, for example. That would work. So what's the probability that a randomly chosen pair of socks, they're all the same color? Well, it's going to be, well, here's the way, all the different number of ways to select 2 socks of the same color. And here's the number of ways of selecting 2 socks in general. You're just going to divide. That's how you calculate the probability, right? So it's this over this. N times n minus 1 over n times 2n minus 1. And so those n's cancel. And the final probability is n minus 1 over 2n minus 1. Okay? So that's the answer there. I hope you got it. So that is our first example for ourselves to try to play with probabilities. And then a new example for you. See if you can figure out which is more likely. Rolling a total of 9 when 2 dice are rolled. So you're rolling some dice and you're like adding together the outcomes that you get. Like maybe you roll a 9 if this happens, right? Maybe you're rolling 2 die. This is my best cube drawing, sorry. You roll a 9 if you get like a 6 and a 3, right? That's one way to do it. So you're rolling 2 die, and what are all the different ways that you can get a 9 in that case? Or is it more likely to roll a total of 9 when you're rolling 3 dice? Okay? So the question is, first, what is the sample space for each experiment? What are all the possible outcomes? Then, what are all the events that we want to see have happen, right? And I've actually written a program for us that's going to make it a bit easier to think about. So, what in the world is the sample space for each experiment? So we're rolling, for example, 2 die. If we're rolling 2 die, what are the outcomes? What's going to happen? So, what are all the different ways that we can roll 2 die? What's the sample space of rolling 2 die? It looks like that could be, well, you can roll 2 die and get both 1s. You could roll 2 die, get a 1 and a 2. You could roll 2 die and get blah, 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 many different options up to 6 and 6, right? So it's all the different pairs, right, of the set 1 to 6, 4, 5, 6, because the first thing of the pair could be 1 through 6, and also the second thing of the pair could be 1 through 6, because it's another die. 1, 2, 3, 4, 5, 6. Okay? That's the idea. Let me bring this all on one line to make it pretty for us to study later. But this is the sample space for rolling 2 die. It's all the pairs, 1 to 6 in the first thing and 1 to 6 in the second thing. Well, it's the sample space of rolling 3 die. That is going to be, well, 1, 2, 3, 4, 5, 6 cubed, right? Because you have 3 options. Each of them can be 1 through 6. So, like, your first option is you roll 3 dice and they're all 1s, or you rolled 3 dice and some are 1s and some are 2s. You have a bunch of options again. So there's definitely a lot more options for rolling 3 dice than for 2. So that's the sample space. What are the events that we care about, right? The event of rolling a 9, right? The event of rolling a 9 when we have 2 dice. What are all the different ways that that could happen? What are all the outcomes that we care about? Well, it could be 3 and 6. That's one way to do it. It could be 4 and 5. That's another way to do it. It could be 5 and 4, because these are 2 separate dice, right? These are different outcomes. And then 6 and 3. There's only 4 different ways to get a 9 with 2 dice, right? So the size of rolling a 9 with 2 dice, the number of outcomes for that, is 4. There are 4 different possibilities, 4 different ways for us to roll a 9 with 2 dice. And we also need to figure out, okay, what in the world is the event that we care about for rolling a 9 with 3 dice? What does this look like? Like maybe a 1, can't be a 1, 1, because then you need a 7, right? It could be 1, 2, and 6, though. That's an option. And this is probably where writing a program would help. So I've written a program to go and enumerate all the possible ways to roll a 9 with 3 dice. So that's here in scratch.racket. And so here I am iterating through all the possibilities. I, j, and k go between 1 and 6. If they add up to be 9, I'm going to output those different ways, and then the count. Okay? Boop. And so let's not worry about this one, but these ones. So here's all the different ways that you could get a 9. It could be 1, 2, and 6, 1, 3, and 5, 1, 4, and 4, all the different ways. And there happen to be, I output the count as well, there happen to be 25 ways to do it. So the size of E3, that event, there are 25 ways to get a 9 with 3 dice. Okay, and so now the question is, what's the probability of each of these events happening, given their sample spaces? Okay, so that means dividing this event by the size of the sample space. That's all the different possibilities that can happen. Each of them are equally likely, uniform distribution. So the probability of rolling a 9 with 2 dice is the size of E2 over the size of S2. Yeah? All the possibilities. And we're going to compare that with the size of E3 over the size of S3. Yeah? So what are those sizes? What's S2 and S3's size? Well, that's pretty easy. S2, the size of it is, well, it's all the different ordered pairs with 6 options in the first pair, 6 options in the first place, and 6 options in the second place. So it's 6 squared options total. Same for S3's size. 6 options and 3 places to put numbers. So it's 6 cubed possibilities. Okay? So it's 4 over 36 versus 25 over 6 cubed is 216. And let's see the difference. 4 over 36, and then 25 over 216. So they're both around 11% chance that each is going to happen, but it looks like with 3 dice it's slightly more probable, 11.6-ish chance. So 3 dice is better. It's more likely, just slightly, but it's more likely with 3 dice of you rolling a 9 than with 2. Okay, do you see how we got there? It's all a bunch of sets. What are the outcomes that we want? What are the events that we care about? And then what is our sample space? Because that's going to tell us all the options, and that's something we can divide by. Okay, so that is a fun example. Definitely study this one and ask me lots of questions about it if it's not making enough sense. Okay, a new example. let's say that we're randomly choosing a number from the set of all the numbers between 1 and 50. Tell me, what in the world is the probability that the integer that you pick at random is divisible by either 3 or by 7? Okay? And here's my hint for you, because you're going to have to use this. You're going to have to use this rule now. Principle of inclusion-exclusion kind of rule. Because there might be some overlap. You need to split the problem into two different events. E3 for divisible by 3, and E7 for divisible by 7. Okay? You need to find the probability of E3 union E7. And it's a good idea to write a program here too. Okay? So give that a try. So what's the probability, or what's E3, for example? What are all the numbers in this set that are divisible by 3? That is your event. If you pick a random one and it's in that set, then it's divisible by 3. So you got your 3, your 6, your 9, your 12, all those numbers, right? Dot, 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 all the way to 48, I think. That's still divisible by 3, yeah, because 8 plus 4 is 12. And then you need to look at E7. What are all the different numbers that are divisible by 7? You have 7, 14, 21. You can just write all these out. 28, 35, 42, 49, right? But there's a 21 in here. You see that? They share things. There is overlap. That's no fun. So we have to do the full probability now. What's the size of E3? What's the size of E7? You can write a program for that. Here's me counting all the numbers that are divisible by 3, 7, and both. I make some code that does that and just output it. So it looks like there's 16 numbers that are divisible by 3. So the size of E3 is 16. The number of numbers that are divisible by 7 and 1 to 50 are, looks like there's 7 of them, right? 7. And then there's 2 that are divisible by both. So the size of E3 intersect E7, there are 2 things that are the same. There is the 21, and then there's also what? Is it 42? Yeah, they also share a 42. 21, a 42, those are also both there, for example. Okay, those are the ones they share, and so we don't want to double count. So the total probability, the probability of E3 union E7 is equal to the probability of E3 happening plus, using the formula, the probability of E7 happening minus the probability of them both happening, because we don't want to double count. And so that's going to be 16 out of 50, right? Because you're choosing from 50 numbers. Plus, what's the size of this? 7 over 50. Chance that you're getting there. Minus 2 over 50. Okay? And so this is 16 plus 5. That's 21 over 50 chance that you're picking a number that's divisible by 3 or by 7. Okay? I hope that makes sense. Yeah, a couple more slides and that'll be it for the day. One last fun real topic of the day is called conditional probability. Okay? Because sometimes you know that 2 things have happened, right? You know that an event F happened, and that gives you a better better knowledge of knowing whether some other event E also happened. Like, hey, if it's wet outside, that means it probably rained, right? You get some extra information. It's more likely if it's wet outside that it had rained the night before, for example. That is standard conditional probability, and you can formalize this in math. Okay? So here is my example diagram that I have promised you with this bullet. So, for example, here is the event, like we care about event E. We want to know, hey, did event E happen? Okay? Like here is everything, every possibility. And here's event E. Like here's all the ways that it could happen. Okay? And, like it might not happen, but there's a good chance. Here are all the different possibilities. Some of them are in E, some are outside. But then, we took a reading, like we looked outside or something, and we noticed that event F, here's event F, we know that event F happened. We are certain of it, okay? And so now we can ask the question, okay, what's the probability of E knowing that event F has happened? Because now it's a bit better, right? We know some different things now, right? Because the probability that event E happened given that event F also happened is like all this stuff in here divided by the total for F, right? You don't have to look at everything anymore. You know you are within F, and you want to see what's the probability of E also having happened, okay? So that kind of gives you a better idea of what's going on, okay? And that could give you a more accurate probability, okay? That's called the conditional probability. It's saying, you write it like this. You say that the probability of E given F. So what's the probability of E given that F has happened? We know that F has happened. And we write it like this. So this little pipe symbol, it means given. So what's the probability of E given F? So what's the probability of E knowing that F has happened? The probability of E occurring when you know that F has occurred. Okay? And so this is how you calculate it. The probability of E given F is the probability of their intersection over the probability of F. Okay? So let me do that for you. So here is the probability of E, for example. Let's calculate all these. Here's the probability of E. That is, well, there's 3 of them over, what's the total number of dots here? 1, 2, 3, 4, 5, 6, 7, 8, 9. 3 over 9. That's 1/3. And what's the probability of F? I'm going to need that. That's going to be, well, we have 1, 2, 3, 4, 5, 6 out of 9. That's 2/3. And then the probability of E intersect F is 2 out of 9. So that's all we need to calculate the conditional probability. So what's the probability of E knowing that F has happened? So that means that that constrains us to here now. You see that? That constrains us to here. And then we calculate, okay, what is all the ways of getting E knowing that F has happened? It's 2, right? 2 out of 6. You see that? So that's one way to calculate probability of E given F. That's 2 out of 6. That's 1/3. And then just to prove that this also, like, that's how it works, this is the way that you can also calculate it. It's probability of the intersection over the probability of just F. That's essentially what we just counted, right? So using the formula now, probability of E given F, that's equal to probability of their intersection, so 2/9 over probability of F, which is 2/3. So do your cross multiplication, that's what, 6 over 18, which is in fact 1/3. So either way works. Okay? Probability of their intersection over the probability of F. Because you know that F happened, you only need to zoom in here now. That's conditional probability. Okay? That's nice to have. And so it looks like the probability of E given F is 1/3. So if I know that F happened, the probability of E also happening, given that I know that F has happened, is 1/3. All right. 2 events, though, are called independent if, when you condition on one event, it does not change the probability of the other event. Okay? And this is an example of independent events. You gained no extra knowledge by knowing that F occurred, did you? Because you immediately, like initially, already knew that the probability of E occurring in the wild, no matter what, is 1/3. And so this was called an independent event because we gained no extra knowledge by conditioning on F. Okay, so sometimes you gain a lot of nice knowledge, other times you don't. Those are called independent events, all right? And there are other ways of noticing that events are independent. So the following 4 bullets are exactly the same. They mean the same thing. So E and F are independent, and that's also if you condition on 1, E given F, calculate that conditional probability, that ends up being equal to the original probability of E. That means it's independent as well. You could also do it the other way. Probability of F given E, that's this probability, if that's equal to just the probability of F again. You gain no knowledge by conditioning on E. That also means that E and F are independent. And then also, finally, if you do enough math, this comes out of these equations, but the probability of E intersect F, that's one way to find it, is to solve this equation for it. If it ends up being the case that probability of E times probability of F equals the probability of their intersection, that means they're independent. Okay? So if they were independent all along, it's very easy to find their intersection, the probability of their intersection, of all of those things happening. Okay? Then you can just multiply. So I told you I'd talk about that again later. Here I am. So that's what it means for events to be independent. Conditioning on them means nothing. Okay? And so that's another important word to remember. And it's very nice for calculating the combined event, the probability that two events both happened, their intersection. You can just multiply in that case. Okay, so that's conditional probability, and let me use it in a very fun example. This is a classic example that everybody teaches when they teach conditional probability. It's a non-trivial problem, it doesn't make enough sense logically, but with enough math, it really works out this way, okay? So here's the game. It's called the Monty Hall game. It's there was some game show, it was British back in the day, and kind of the idea was you are a contestant in a game show, and there are 3 doors. Okay, there's door 1, door 2, and door 3, and here's their little door handles. You can choose to open any door, okay? The idea is there is a car behind one of these doors, and here's my horrible drawing of a car. There's a car behind one of these doors, and there is a goat behind the other 2. Okay, so 2 doors have goats, 1 door has a nice car, and you get to make a guess. You get to say, I think the car is in door number, what's the right thing? Let's say that we make the guess that we think that the car is in door number 2. Okay, so that's our guess. So the contestant on the game show gets to make a guess like this, and then Monty Hall, which was apparently the person who was in charge of this game show, the announcer, he went and opened another door with a goat in it. So if you pick door 2, Monty will go and open door 3 and show you that, hey, there was a goat in door 3. That was not the one that you picked. And now he asks you, do you want to change your guess from door 2 to door 1? Would you like to swap your guess, because you only have one other possible door to open now, or would you like to stay with your original guess of 2? Which one do you think the car is behind now? So you make the guess of 2, Monty opens one of the other doors that definitely has a goat, and now you have these 2 possibilities left, where 2 was your original choice. You have the choice now of swapping your guess to door 1 or staying with your guess of door 2. And the question is it better to swap or to stay? It turns out that these are not the same. You actually are better off always swapping. Okay? And let me show you why. The probability that, the probability that you got the car in the right spot on the first round, right? The probability of you staying with your original guess and getting the car, that ends up being 1/3, because what's the probability right before you had any information at all that you guessed the right door? It is 1/3, right? You have no information, it's behind one of 3 doors. The probability of you making the first guess originally correctly is 1/3. Now the weird thing happens is when you switch. The probability of switching and getting the car. And let me give you the hand-wavy proof of how this works. It is very unintuitive, but it ends up being 2/3. And here's the reason. So, because originally you make a guess, you're not sure, right? you're not sure where this car is, but you make the guess of door 2. That means there's a 1/3 chance it's behind door 2, and there's a 2/3 chance it's not behind door 2. You see that? There's a 2/3 chance it's not behind door 2. And Monty's guaranteed to open the goat door, and so the other door gets all of that other 2/3 probability of it being the correct door. That's my hand wavy proof. Does that make sense? So that is the probability of you not getting the guess right is 2/3, and that means the other door that you could switch to is more likely. It has a 2/3 chance of you getting the car. Isn't that cool? That's completely unintuitive, but that's a nice example of events that can be combined like this. And to think about it, it's not at all intuitive, but hopefully my example or my words made it make enough sense. So I made a simulation in Racket just to prove it to you that this is correct. Like, this is the correct solution to the Monty Hall problem. It is always better to switch. And here is that. So I've made a simulation program. So I'm going to make 1,000,000 simulations, and I'm going to count all the number of times that you end up winning by staying and not changing your guess, and all the number of times that you end up winning if you were to have changed your guess. Okay, so I simulate by picking a random door with a car in it and picking a random door that we end up picking, and then I calculate, like, okay, did we win, did we not win? Okay, and I keep track of that in my simulations with randomness, and then here is the outcome. So it's running 1,000,000 simulations, and, well, this is how many wins you get by staying, and this is how many wins you get by changing your guess. It is 2/3 and 1/3. Isn't that so cool? So yeah, if you're ever on this game show, you always want to switch. That's Monty Hall. That's intersections of events, not quite conditional probabilities yet, but let me give you some conditional probability questions now, and that'll be it for the day. So here are some letters, A, B, C, D, E, F, G. That's a set of them. Let's say that we put those letters in a random order, okay? So that means we're making permutations of those characters. So we're putting all those letters in random orders. And so for example, one possible outcome is like A, D, C, B, G, F, E. That's one possible permutation. Every possible permutation is equally likely, and here are 3 different events. Okay? Event A, the letter B is right in the middle of your permutation. It's right here. That's one way to do it. There are a bunch of others. Okay, so that's event A, where B is always in the middle. Event B is the letter C appears to the right of B somehow, though it doesn't have to immediately be to the right of B. It could be, but it doesn't have to be. So for example, this permutation, A, B, D, C, E, F, because B is somewhere before C. That is a possible outcome. Okay, that's part of this event. That's something we care about. Okay, that's event B. C is somewhere to the right of B. It doesn't have to be immediately after it, but it is somewhere over there. B comes before it. And then event C is the letters D, E, F occur together in that order somewhere in your permutation, in your final string. So for example, this is a string that would be in event C. So those are your 3 events, and I would like you to calculate first the probability of each of them. So PA, PB, PC. Then, using our rules, calculate A given C. Like, do you get any extra information knowing that your string looks like this with D, E, F in order? Do you get more information about the probability of A, about B being in the middle? Same for the probability of A given B, and then with that in mind, you can calculate, hey, are the events A and B, or are the events A and C, are they independent to each other? So try all that, and then I'll do it with you. All right, so let's do the first one. Let's do problem A. So let's calculate the probability of A, event A occurring. And so we essentially take all the ways that you could make this happen and divide it by all the different possible permutations that you can make, right? So the letter B is somewhere in the middle. That means you have already picked that B goes in the middle, and the only other things that you need to choose from, the only other possibilities, the only things you need to count are what do you put on the other sides, the other 6 characters, right? So how do you arrange the other 6 characters in order? So you're calculating permutations. You're making a permutation of 6 characters now, because B is forced to be in the middle. There are 6 factorial ways to do that, and 7 factorial ways to arrange all of them. Okay? So that's the probability of A. There are 7 factorial total permutations, because there are 7 characters. So that's the probability of A. Probability of B now, event B, is, okay, C appears to the right of B, but it doesn't have to immediately be to the right of B. And if you think about it, well, all the different ways that you do this, sometimes when you generate your permutations, B is on the left of C. Sometimes when you generate your permutations, B is on the right of C. But if you think about this long enough, there are an equal number of these permutations to these permutations. There's a 50-50 chance that C is on the right of B or it's on the left of B. Does that make sense? So that means event B, where C is on the right, there's a, like it's a 50% chance. There's only half of the possibilities where that is true. Yeah? Because it's either on the left and on the right. All the permutations, it doesn't really matter. You're enumerating over all of them. There's no preference. So half of them are on the left, half of them are on the right. It's a 50% chance that C appears to the right of B. Okay, so that's the probability of event B. And then finally, the probability of event C is, all right, D, E, F occur together in order somewhere. Okay, so that is, again, well, you have to pick, all right, you just treat D, E, F like one big character. Does that make sense? You just treat it like one big character. D, E, F is one big char now. And so we have 1, 2, 3, 4, 5 characters to permute now. Does that make sense? That's how you calculate the number of ways to do this. So there are 5 factorial different orderings of those 5 quote characters, right? And 7 factorial permutations of the characters total. So that's the probability of C. Okay? So that's how you get each of those. And now we can use that to calculate A given C. Okay, so what's the probability of A given C? That is, going back to the definition, it's the probability of their intersection over the probability of C. So we need to figure this out. What in the world is this probability? What's their combined probability? What are the chances? What are all the different ways of getting B in the middle and also D, E, F occurring? So this becomes a question of, okay, what are all the different ways to have B in the middle? You're forced to have B in the middle, and then D, E, F in order. So D, E, F is 3 characters, and you need to put 3 over here and 3 over here. So the D, E, F could be here. That's one way to do it. And then you have to figure out what the rest of the characters should be. Or B is in the middle, and D, E, F is over here, right? Because they have to be in order. And then you have to figure out what these characters should be. So there are now, like you've made this choice, you've put it first, you just have to worry about the other characters. There are 3 factorial of these permutations that look like this, because you just have to put the rest of the 3 characters remaining in some random order. There are 3 factorial possible orders. Same for this one. You've chosen that B, D, E, F is the end of the string. You just need to arrange the remaining 3 characters in some way. 3 factorial. Okay? So the probability of A and C both happening is, well, 3 factorial one way plus 3 factorial for the other way over 7 factorial. Okay? Because that's the total possible number of permutations. So that's the probability of A intersect C. And then you just divide that by the probability of C, which we've already calculated. Okay? I won't do the rest of this, but that is how you get that. Okay? I hope that makes sense. These are definitely harder examples, but they are good practice. Okay? So I hope you thought about these before you watched me do them. So that's part B. Let's do part C now. What's the probability of A given B? And so this is going to be following the pattern, following the definition. We calculate the intersection, probability of A intersect B, over the probability of B itself. Okay? So, again, both of these happening at once. So B is smack in the middle, and C appears to the right of B. Okay? But it doesn't have to be immediately to the right. So how do we figure this one out? Let's go and draw out an example again. So B is in the middle. We have forced B to be in the middle, and then you have to pick characters that go here, 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 and here, right? You know, if we are in event B, that is the correct one, right? That C is on the right. C must be over here somewhere, okay? So how many ways are there to put C over here in one of these? You have to pick one of those three options, right? So maybe we put the C here, but it can only go in 3 places. 3, yeah? So that's part of this. And then the question is, okay, how many ways are there to place the rest of the characters? So we found the place for the C to go. It must go there. I'm going to put the C right there. And then I need to place the rest of the 5 characters in some random order, some random permutation. So 5 factorial, because there's 5 things to permute. 5 characters left. Does that make sense? And so the probability of that intersection is 3 times 5 factorial, all over 7 factorial. Okay? 3 times 5 factorial over 7 factorial. And then that is over the probability of B. Okay, so that you can also calculate. I won't do it. But now that we've calculated these things, let's see. Is it true? Is it the case that A and B are independent, or A and C are independent? Going back to this definition, because we calculated these probabilities, it's independent if the conditional probability is just the probability of that first thing. Okay? So is it the case that probability of A given C, is that equal to the probability of A? So this is part D. So is the probability of A given C, is that equal to the probability of A? How does that compare? And is the probability of A given B equal to the probability of B? And I won't do the math, but it turns out that these are not equal, and these are. Okay? So that means that A and C are not independent, but A and B are independent of each other. So you gain no knowledge knowing that like B happened. You gain no knowledge over whether event A happened as well. That's pretty cool. But A given C, that is not independent. So you gain some knowledge by knowing that C has happened. You know that D, E, F occur. That tells you a lot about, hey, did B fall in the middle or not? Okay, so that is our first taste of probability. I've got more for you, of course. We've got a whole nother lecture on this, but that's the first one. A lot of new things, a lot of new terms. Definitely study them, study the examples, and I will finish these slides up next week, so I'll see you then.